Sinovac, di ba?
Hindi pa po yata dumarating.
Parang wala akong narinig na nakipagkontrata na sila. Ang narinig ko lang nakapagkontrata yung group yung AstraZeneca ni Concepcion, tsaka yung Moderna, di ba?
Ay, sa negosyo po ba yun? Yun po ba yun?
Yung kay Concepcion, oo. Moderna
yung
kay...
Yung ibang Sinovac, purchase na yung ma'am eh.
Ay, yung sa China? Oo. Yeah. Well, sabi nila, just get the vaccine that's available kasi it prevents severe case and death. Then sabi naman iba, most likely, baka parang flu vaccine that you get every year. Kasi hindi pa nag-change yung variant.
Kaya, important lang ma-reduce yung hospitalization.
I-manage yung?
Ma-reduce yung hospitalization.
Grabe, no? Sa case ko, parang yun ang mga close friends and relatives ang nako-COVID na. Dati yung mga kilala pa lang, mga friends ang kilala, gano'n. Yung medyo malayo pa. Ngayon talagang almost sa home. Okay, let's start. So, Charles, how far have they gone sa Sure? May example na sila ng ano?
Ma'am? Yung sa discussion na prepare ko, meron doon na pinagawa ko na on their own na
sige.
Exercises sa Sure.
Okay, good. Okay. So we move on to simultaneous equations. Okay, so I'll share screen. Charles, nakuha na ba nila itong file?
Oh, yes, ma'am. Uploaded na.
Okay, so okay, so this is our third major topic. The first topic was instrumental variables and two-stage least squares in the context of single equations. Then we went to systems of equations and we took their GLS and the Schur model. We move on to the simultaneous equations model. So today, most likely I'll cover only up to identification. So I'll go to the introduction and the identification problem for simultaneous equations model. And hopefully on Thursday, we'll go through the rest of the topics: estimation, cross-equation restrictions, and covariance restrictions. So as we go along, you will notice that the concepts we use are just repetitions of what we have used before. Okay, for simultaneous equations, we consider as a set of linear equations. So we're limiting ourselves to linear equations that determines jointly a set of G outcomes where endogenous variables may appear on the right-hand side with exogenous variables. Okay. Okay, since we have endogenous variables appearing on the right-hand side, then we get again into the endogeneity problem. Okay. So what did we have before? When we had instrumental variables, we said that when some right-hand side variables are endogenous, that is correlated with the disturbance term, then we can get biased estimators of the parameters. And that problem of correlation between the endogenous variable and the disturbance term can occur when we have omitted variables, simultaneity problem, and measurement errors. Okay. Notice that only the statistical structure, as we go into the identification problem and the estimation approaches, only the statistical structure is important. Okay, so we're abstracting from omitted variables. A common example in simultaneous equation models would be systems of demand and supply of goods, where we jointly determine quantities and prices. So the observed prices, the observed quantities and prices reflected in the data are actually equilibrium outcomes already. Okay. Let's have a couple of examples of the simultaneous equations model. Okay. For our first example, in Woolridge book and other econometrics work, you would often see this labor supply and wage offer system for married women. Okay, so the first equation here is this first equation is the labor supply equation. Okay, so H is hours work, W is wage, but note that wage is also a left-hand side variable in the other equation. Okay. So wage is an endogenous variable. Then we have the other control variables, experience squared, other income, and number of children, kids. Okay. So this squared term is not a problem, right? You just treat that as any other exogenous variable. Okay. For the wage offer equation, we have wage is determined by hours work, experience squared, and education. Okay. Note that, so here we have other sources of income and number of children affect the labor supply, but it does not affect the wage. Okay. And on the other hand, education affects the wage offer, but not the labor supply. Okay. In these simultaneous equations models, you have to also make sure that your equations make economic sense. So usually the specification of these equations are also driven by economic theory. Okay. But we do estimation because we really do not know the parameters of these equations. Okay. In this system, we have two endogenous variables, H and W. Okay. The idea of an underlying counterfactual is critical to sensible applications of simultaneous equation models. Okay. So for example, we might want to see what is the effect of wage on hours worked, keeping experience, other income, and kids constant. Okay. There are some models where it does not make sense to hold constant the other explanatory variables. Okay. I think Wooldridge should have some examples of that. Okay. So it makes sense to think of a demand function in isolation. Okay. And so the demand function is this wage offers equation. And we have the labor supply function as the first equation. Okay. So these two equations are brought together as a way of determining the observed data or equilibrium points. So these H and W are actually equilibrium points already. Okay. So you have assumed already the equilibrium of supply and demand. Okay. Another example, this is also an often cited example, is city crime rates and the size of the police workforce. Okay, so we have the endogenous variables are crime, this is the crime rate, and we have police, a measure of some variable on police enforcement. Okay. So each equation stands on its own. The two equations form a legitimate simultaneous equation model. Okay, so we have here what is the effect on crime rate of police enforcement. Age, I think this would be some age indicator of for the city. This can be the median age and the unemployment rate in the city, and also the average wage rate in the city. For the second equation, this is a measure of police enforcement, but police enforcement is also a function of crime. Well, usually if there is a higher crime rate, you would expect that there would be a higher police presence. Okay. Then we have the other variables, age, unemployment, and wage, which also appears in the first equation. And we have this other variable, election. Okay, this would be, I guess it depends on the unit of observation if it is for an election year. Okay. Okay, so note that here, these two equations come together as a system under assumptions about the observed crime and police. So those are two examples of simultaneous equations. So they're pretty simple because we just have two equations. Okay. Okay, let's go to the identification problem. Okay, so for identification, we'll first take the easy case where we just have two equations in the model, so that we would have some intuitive feel of what is going on. And then we'll take the general case of having G equations or G endogenous variables. Okay. Note that identification is a feature of the population. Sampling is a separate issue. That's why as we go through the lecture, our model is in terms of the population model. Okay. Okay, sampling might come in when we go into estimation. Okay. Though certain sampling schemes can cause lack of identification, but for now, we will abstract again from this potential problem. Okay. So we start with the population as the starting point, okay? And we assume we're doing random sampling. Okay? So let's have a two equation system. The general two equation structural system, so this describes the population, is given by this system of two equations. Okay, so we have two endogenous variables, y sub 1 and y sub 2. Okay, okay, so just by the specification, you know that if this is the true population model, the disturbance term would affect y sub 1, u sub 1 would affect y sub 1, u sub 2 would affect y sub 2. Okay. But then here also you would see that y sub 1 is affected not only by u sub 1, but also by u sub 2 because y sub 2 affects y sub 1. So if you substitute y sub 2 in this expression, you would get u sub 2 affecting y sub 1 also. So in the same manner, u sub 1 would be also affecting y sub 2. Okay, so we have in boldface vectors and matrices. C1 is the set of exogenous variables in the first equation. And we're assuming that we have m sub 1 of those. C2 is the set of exogenous variables in the second equation. And we're assuming we have m sub 2. Okay. Y sub 1 is 1 by 1. C sub 1 is 1 by m sub 1. So this delta sub 1 would be m sub 1 by 1. So that is a column vector. So this is a row vector multiplied by a column vector, and you get a 1 by 1 term. Okay. The same thing with C sub 2, delta sub 2. Okay. Then let us form the row vector Z to contain all non-redundant exogenous variables. Okay, so if some of the variables in C sub 1 appear in C sub 2, you just specify it once. Okay, so M is not necessarily M sub 1 plus M sub 2. Okay. We assume that the Z's are exogenous variables. So we have these orthogonality conditions. The expected value of C transpose U sub 1 is 0. The expected value of C transpose U sub 2 is 0. Okay. This 0 here, this is a 0 vector of dimension m by 1. So this has m rows by and 1 column. Okay. Okay. Note that this is C transpose. So this is m by C transpose is m by 1. So you multiply this, the components of this column vector by U sub 1, which is just 1 by 1. Okay. In almost all applications, C sub 1 and C sub 2, and therefore Z, include unity. Okay. And we include this unity so that the non-zero components of the disturbances would be absorbed by the intercepts. Okay. If so, then the structural errors, U sub 1, U sub 2, we can assume to have 0 means. Okay. Okay. Note that the moment conditions, these are the moment conditions. Okay. So we have 2m moment conditions, they imply that if a variable is exogenous in any equation, it is exogenous in all equations. So for example, if age is exogenous in the first equation, it is also exogenous in the second equation. Okay. We have election here appearing in the second equation, but it does not appear in the first equation. Election is uncorrelated with u sub 2, and also it is uncorrelated with u sub 1, because we assume that this is an exogenous variable. And that follows from this assumption. Okay, so what are the structural parameters that we would like to estimate in this system of two equations? So that would be gamma sub 1, gamma sub 2, delta sub 1, and delta sub 2. Okay. So we have M1 plus M2, M sub 1 plus M sub 2 plus 2 parameters of interest. Okay. We do not really need the reduced forms to study the identification, but the reduced forms can be obtained if gamma sub 1, gamma sub 2 is not equal to 1. And we will see that later. Okay. Let's go through the reduced form. Okay. A reduced form expresses an endogenous variable as a function of exogenous variables and unobserved errors. So at the left-hand side, you have an exogenous variable. So here, you would have y sub 1 on the left hand. For the first equation, y sub 1 is an endogenous variable. And on the right-hand side, we should just have purely exogenous variables and the unobserved errors. Okay, so let's get the reduced form for y sub 1. Okay, so this is the equation for y sub 1. Okay, so we substitute the second equation for y sub 2. Okay, so we would have gamma sub 1, then this is the expression for y sub 2 plus c sub 1 delta 1 plus u sub 1. Okay, then we gather terms. We just carry out the multiplication and we have this expression. Okay, so note that in this form, y sub 1, the endogenous variable, has a coefficient 1 on the left-hand side. On the right-hand side, it still appears here. Okay, you still have y sub 1 here. Then you have the endogenous variables, c sub 1, c sub 2. Okay. Therefore, if we have okay, we want y sub 1 to appear only on the left-hand side. Therefore, you bring this term to the left-hand side. You would have this factor 1 minus gamma 1, gamma 2 in the denominator. But when you bring it to the right-hand side, then you have the inverse, okay? Or you just get the reciprocal of this number. And then you have c sub 1, delta 1 plus c sub 2, gamma 1, delta 2, plus this sum of the disturbances from the two equations, okay? So we can re-express this as z pi sub 1 plus v sub 1, where, okay, so you would have z would consist of c sub 1 and c sub 2, and pi sub 1 would consist of the terms delta sub 1, gamma sub 1, delta sub 2 divided by this expression. Okay. And then you have the no disturbance term. Okay. Okay, so now we have an m by 1 vector of reduced form parameters pi sub 1. Okay, because z is of dimension 1 by m. Okay, so the associated parameter vector is m by 1. And the reduced form error is this u sub 1 plus gamma 1 u sub 2 multiplied by this inverse. Okay. Therefore, if you do the same manipulation for y sub 2, then you would have these two equations. And this would be the reduced form. Okay, so that is the reduced form. And here you have the moment conditions. The expected value of C transpose V sub 1 is equal to the expected value of C transpose V sub 2 is equal to the 0 vector. Okay, so that says that this Z is uncorrelated with V sub 1. This Z is also uncorrelated with V sub 2. But note that these some of the Z's here do not necessarily appear in the second structural equation. Also, some of the Z's may not appear in the first structural equation. Okay. So how would you estimate these reduced form equations if you want to estimate pi sub 1 and pi sub 2? How would you estimate? Okay. First, I want to, as an exercise, you don't have to submit, show why these moment conditions would be true. Okay. That's easy to show because V sub 1 like V sub 1 would just be this expression. Okay. Then you get the corresponding reduced form error for this second equation, V sub 2. But note that these are functions of U sub 1 and U sub 2. Okay. So try to show why this holds. Okay. So note that pi sub 1 and pi sub 2 can be consistently estimated by OLS on a random sample provided the expected value of C transpose Z is non-singular. Okay. Why can it be consistently estimated by OLS? Well, if you do estimation by OLS, you're really doing OLS equation by equation, right? And you can do that because Z is uncorrelated with the disturbance term. Okay, so you can estimate the first equation by OLS, the second equation also by OLS. You get OLS estimators for pi sub 1 and pi sub 2. Okay, and why do you require the expected value of C transpose Z to be non-singular? Okay. Note that this is the population moment. Okay. Also, sure estimation would not improve estimation of the reduced form parameters. Okay. So even if you run this by using sure, you would get the same estimates. You would not be improving estimation of the reduced form parameters. Okay. So see why not? Why sure would not give you improved estimators. Okay, so that is the reduced form. Let's go back to the question of identification, wherein we ask, when are the structural parameters identified? That is, if the structural parameters are not identified, then we cannot estimate the structural parameters. The structural parameters being these ones, okay? Okay, we're interested in the structural equations, okay? Not in the reduced form equations, okay? For those who are doing papers that involve econometrics, sometimes the models are used that does not really have strong theoretical underpinnings. So they just start with reduced form equations rather than structural equations. Okay. Ideally, you should start with structural equations, okay, and not the reduced form equations. Because generally, if you have reduced form equations, it's not clear what the economics is behind your equations. Okay, so going back to the identification problem, let's consider the identification of the first structural equation. So write the first structural equation with the reduced form for the second endogenous variable, okay? So this is the structural equation for the first endogenous variable, y sub 1. Okay, so I just picked up the first equation here. And then for y sub 2, I have the reduced form. Okay, y sub 2 equals c pi sub 2 plus v sub 2. Okay, so it is just this. Okay. Okay, so note that since y sub 2 is the only endogenous explanatory variable in the first equation, okay, y sub 2 is an endogenous variable, then we need at least one instrument for it, right? Y sub 2 would be correlated with u sub 1, okay? You can see that here also, y sub 2 would be correlated with v sub 2, the disturbance term, but then v sub 2 would be a function of u sub 1 and u sub 2. Okay. Okay, so we need an instrument for y sub 2, the endogenous variable. That means we must have something in z in the reduced form here with a non-zero coefficient that is also not in C sub 1, okay? So there must be an exogenous variable in this Z vector, which is not in C sub 1, that has a non-zero coefficient in this vector pi sub 2, okay? But here we see y sub 2 is gamma sub 2, y sub 1 plus c sub 2, delta 2 plus u sub 2, okay? And so pi sub 2 has a non-zero coefficient of on something not in Z1 if and only if there is at least one element of Z2 that is not also in Z1 with non-zero coefficient in delta 2. Okay. Well, that is also what we had in instrumental variables, right? Y sub 2 is endogenous. So we want an instrument for y sub 2 that is correlated with y sub 2. So that instrument must be in C sub 2, but not in C sub 1, okay? And for C sub 2 to be correlated with y sub 2, its associated coefficient, which appears in delta sub 2, must be non-zero, okay? In summary, we can read the identification of each equation of the structural system, okay? So the first equation is identified if and only if there is at least one element in C sub 2, not in C sub 1, with a non-zero coefficient in delta sub 2 in the second equation, okay? Similarly, the second equation is identified, okay? Y sub 1 is an endogenous variable. We want an instrument for y sub 1. So there must be some variable in C sub 1 with non-zero coefficient that does not appear in C sub 2. Okay, let's go back to the first example. Okay. The first structural equation is the labor supply function. Note that we're just looking at the structural equations here, not the reduced form. And in this simple two equation system, we do not need to look at the reduced form. Okay. So the first, we have labor supply. Okay. So what is in Z that is not in the first equation? Okay, and so that would be education is an exogenous variable. So this is in Z. So for education to act as an instrument for W here, delta sub 23 must not be equal to 0. Okay. So the labor supply function is identified if and only if delta sub 23 is not equal to 0. The wage offer function, this is the second structural equation, is identified if at least either other income or kids have non-zero coefficient, or it can be both having non-zero coefficients. Okay. In the in the first equation. Okay. Is that clear?
Yes, po.
So know that the reasoning is very similar to what we had for instrumental variables. Okay. Imposing the exclusion restriction means that it must be the case that education is legitimately excluded from the supply equation. Okay, this is the supply equation. So it must be that education is legitimately excluded. That is, in the population, if you included education in the first equation, its coefficient in the first equation would be 0. Okay, so in the population, the coefficient of education in the first equation would be 0. That's why it does not appear in the first equation. Similarly, in the wage offer equation, if you included other income and kids in this equation, their coefficients in the population is actually 0. Okay, that's the sense in which other income and kids are properly excluded from the wage offer equation. Okay, so that is an assumption that we have the correct specification. Okay, so in this case then, if you want a single equation method, you can estimate each equation separately using two-stage least squares, right? So you can estimate this labor supply equation. W is endogenous, and the instrument you use is education. Okay. You can estimate the second equation using two-stage least squares. H is endogenous, and the instruments you use would be other income or kids or both. Okay. Okay, so know that in general, identification of any particular equation of an simultaneous equation model depends on the structure of other equations in the SEM. Okay. Okay. When we go to the more general case, when we go to the estimation part, then we would look at other system approaches to estimating the simultaneous equations model. Okay. So let's generalize to a system of G and endogenous variables. So we have G equations. Okay. So first of all, when you specify the model, make sure the system of structural equations makes economic sense. Okay. And identification analysis will come up with the rank condition, the order condition, the normalization restriction. It just becomes purely mechanical. Okay, so let's first lay out the notation. Okay, so we have the set of endogenous variables. We have G endogenous variables. So we have, this is a row vector, y sub 1, y sub 2, down to y sub G. Then we have M exogenous variables, C sub 1, C sub 2, down to C sub M. And then we have, okay, so this covers all the all the exogenous variables in the system. Okay. And U, we have G endogenous variables. We have G equations. So we have G structural errors, U sub 1, U sub 2, down to U sub G. Okay. In matrix notation, we can write it in this form. Okay. Okay. Note that we have G equations here. Okay. So we have Y gamma sub 1 plus Z delta sub 1 plus U sub 1 is equal to 0. So Y here is 1 by G. So this gamma sub 1 is G by 1. So you have a parameter for each of the Y's. And then you have, for the endogenous variables, you have M of this. This is a 1 by M vector. Therefore, you have a column vector with M rows delta sub 1. Okay. So if you carry out this multiplication, you get 1 by 1 term. U sub 1 is 1 by 1. And you have this 0 is also 1 by 1. This is one form of the simultaneous equation in matrix notation, okay, where I have G equations, okay. Later on, we will collapse this into another matrix form, okay. So note that this setup allows for traditional specification of supply and demand, okay, where Y sub 1 quantity, can be on the left-hand side of both equations with Y sub 2 price on the right-hand side in both equations. So don't be surprised if you would sometimes see the model written in this form. You have Y sub 1 at the left-hand side for the first equation and also for the second equation. Okay. Because you can always re-express the equation. Okay, so for example, here, for the labor supply, you could have written H at the left-hand side, W on the right-hand side also. Okay. In each equation G, so for a specific equation, so G, lowercase g, can go from 1 to up to uppercase G, okay? So gamma sub G is G by 1, okay? Because you have big G endogenous variables, and sigma sub G is M by 1 because you have M of these exogenous variables, okay? So here, the way we specify the model, we assume that Z is exogenous. Therefore, Z must be uncorrelated with the disturbance term. So this Z is uncorrelated with U sub 1, this Z is uncorrelated with U sub 2, down to Z is uncorrelated with U sub G. Or you can write it compactly as the expected value of C transpose U sub G is 0, M by 1, okay? Where C transpose is the transpose of this row vector. Okay. So note that this would consist of G times M moment conditions, right? Because you have, for each equation, you would have big M moment conditions. Okay. You would have a moment condition for each of these C. So for example, for the first equation, C sub 1 is uncorrelated with U sub 1, C sub 2 is uncorrelated with U sub 1, C sub M is uncorrelated with U sub 1. Therefore, you have M moment conditions, okay? But that relationship must be similarly true for the other equations. So you have for the, let's say the second equation, u sub 2 is uncorrelated with u sub c sub 1. U sub 2 is uncorrelated with c sub 2. U sub 2 is uncorrelated with c sub m. Okay. Therefore, how many moment conditions do we have? We have G times M moment conditions. Okay. And then we assume that the expected value of C transpose Z is non-singular. Just to ensure the feasibility of the estimator, that we can calculate the estimator. But how many parameters, structural parameters do we have? Okay. So for each equation, how many parameters do we have? Okay, so gamma sub G is G by 1. Delta sub G is M by 1. So you have G plus M parameters in an equation G. Okay, so that is where your G plus M comes in. But then you have G uppercase G or big G equation. So you have G times G plus M structural parameters. Okay. But we only have GM moment conditions. Okay. So the structural parameters would be G squared plus GM. So we have an extra G squared structural parameters above the GM moment conditions. Okay. So that means that we need to put in some restrictions on the parameters in order to estimate the structural parameters. So we have to put restrictions on the structural parameters, okay? And basically that is, we're putting in more information via those restrictions, okay? Let's look at the reduced form for this general system of G equations. Okay, rewrite the system of all G equations. Okay, so this is our system of G equations. We rewrite it in a more compact form in this way. Y is this gamma plus C delta plus U, uppercase gamma, uppercase delta plus U. Okay. So here, gamma is G by G, and it consists of gamma sub 1, gamma sub 2, gamma sub G. So you have G columns. You have G columns and you also have G rows. Okay. So you're just putting these parameters, gamma sub 1, gamma sub 2, gamma sub G, as columns in this bigger matrix. Okay. And delta here would have elements delta sub 1, delta 2, delta sub G. You just put this as columns in that delta matrix. Okay. And U, well, what would be the dimension of Y? Y is 1 by G, gamma is G by G. So this U would be 1 by G. So that U would be having as columns U sub 1, U sub 2, down to U sub, down to down the columns U sub G. And let us assume that gamma is non-singular so that the reduced form exists, okay? We will be needing the inverse of gamma, okay? Then define the G by G. So note that you have these errors. Okay, U here is 1 by G. So U transpose U would be G by G, okay? Let us get the expected value of U transpose U denoted by sigma, okay? That's why I have this, just this defined symbol, okay? Note that this is the variance covariance matrix. We have, you can write it in this form because we have assumed that the means are 0, okay? And that is innocuous if you have the intercept in the model. Now let us get the reduced form for this, okay? So this is the structural equation. Let us get the reduced form. So for the reduced form, we want to isolate Y on the left-hand side and have Z and U on the right-hand side, okay? Okay, so again, this is the structural equation. Okay, we want to get the reduced form wherein Y appears on the left-hand side and on the right-hand side, we have Z and U, okay? Okay, so how do we do that? Okay, so rewriting this equation, okay, so Y gamma is equal to minus C delta minus U, okay? Okay, so here is where the assumption that gamma is non-singular comes in because we'll be using the inverse, okay? So post-multiply both sides of the equation by gamma inverse, okay? So at the left-hand side, we're left with, excuse me. I'm about to run out of power. I'll just turn it on. Okay, so be careful, the order of multiplication matters, okay? Okay, so if you post multiply the left-hand side here with gamma inverse, then you just get Y, okay? But you have to post multiply each of these terms by gamma inverse. So I have gamma inverse here, okay? So this minus sign I just put in here, okay? So I have some expression in terms of Z and U, okay? Therefore, I can define this as Z times pi, where I define pi as minus delta sigma inverse, and V, the disturbance term in the reduced form equation, is U times minus sigma inverse, okay? Okay, so this is the reduced form, okay? Note that for this reduced form, the disturbance term, we would like to get the variance covariance matrix of V, okay? So the variance covariance matrix of V, that would be a G by G matrix, would be this. So that would be the expected value of V transpose V. Let us define that as lambda, and that would be equal to gamma inverse transpose sigma gamma inverse. So I'd like you to show that. Again, that is not difficult. You just use this definition of V, okay? Okay, this sigma appears here because that would be the variance covariance matrix of the use. Okay, because C transpose V, the expected value of C transpose V is equal to 0, and we assume that the expected value of C transpose Z is non-singular, then pi and lambda would be always identified. That is, the reduced form parameters are identified. Okay. So again, you can just do OLS equation by equation, okay? Because the C's would be uncorrelated with the U's. Let's go to the question of identification in the context of a system of G simultaneous equations. Okay, so in identification, we would like to look at when we can recover the structural parameters, gamma, delta, sigma, from the reduced form parameters. Okay. So here I have sigma. Sigma is of interest, but not usually. Okay. If we can estimate all elements of gamma, then we can estimate sigma using this relationship. Okay. What is gamma? Gamma is just this. Okay. There are the coefficients of the endogenous variables. Now, let's have matrix F as any G by G non-singular matrix. Okay, so F inverse exists. Okay, let's post-multiply the structural system by F. Okay, so the structural system is this. Okay, so we post-multiply both sides of the equation by F. Okay, so we have Y gamma F plus C delta F plus UF is equal to 0. Okay. And let us define gamma star as gamma F, lambda star as delta F, U star as UF. Okay. So this is the transform system when we post-multiply the initial structural equation by F. Okay. So note that this is of the form, this form is similar to this, except that we have starred variables. Okay. So we have starred variables for the coefficients of Y, the coefficients of Z, and the disturbance state. Okay. Okay, so from this equation, okay, so from this equation, okay, so I just isolate Y gamma star on the left-hand side. So I have minus C delta star minus U star, okay? And then I post multiply by gamma star inverse, okay? Both sides of the equation. Gamma star inverse would exist because gamma star is gamma F. Gamma is non-singular. F is also assumed to be non-singular. Okay. Okay, we have assumed gamma to be non-singular. Right? Here, gamma is non-singular. And F is also non-singular. Okay, so we just use the old trick as before. So we get this expression, this line, okay? And then for this line, I just substitute the expressions for the star variable. So for delta star, that is delta F. So delta star is delta F. Lambda star inverse, okay? So lambda star inverse is just the inverse of lambda F. So that is F inverse lambda inverse. Okay. When you're getting the inverse, you reverse the order. Okay. So you have this. Then same thing here. You have U star. U star is UF. So I have U and an F here. And then lambda inverse star is F inverse gamma inverse. Okay. So this F times F inverse gives you the identity matrix. So you're left with Z is equal to minus delta F inverse plus U minus gamma inverse. But this is the original system before we post-multiplied by F. Okay. So this system gives you the same result as the original system, okay? So you get the same reduced form. Okay, so the reduced form of the new system is the same reduced form of the original system. Okay, since the transformed system is indistinguishable from the original system, we say that the transformed system is just an equivalent structure. Okay, so it does not give you any new information. Is it? Okay. So for identification, we need to place restrictions on gamma, delta, and sigma. So there are no equivalent structures. Okay. Let us define this new matrix B, which is G plus M by G. So this would be the matrix of the coefficients. Gamma, would be the coefficients of the endogenous variables. Delta would be the coefficients of the exogenous variables. That's why you have G plus M rows. And then you have G columns because you have G equations. Okay. Okay. So this B is a G plus M by G matrix of structural parameters on the endogenous and exogenous variables. A G by G non-singular matrix F is an admissible linear structure if these two conditions are satisfied. BF satisfies all of the restrictions B does, F is just any non-singular G by G matrix. F transpose sigma F satisfies all the restrictions sigma does. Okay. So we need to have enough restrictions on B and sigma so that the only admissible linear structure is F, which is the F equal to the identity matrix, the G by G identity matrix. Okay. In cross-section settings, sigma is rarely restricted, the variance covariance matrix of this references. So for now, we will just be imposing restrictions on B, the coefficients of the endogenous and exogenous variables. Okay, this is an important step for testing for identification. Okay, we need to have the normalization restriction. Okay. Consider the identification of the first equation. You just do a similar thing for the other equations. Assuming no cross equation restrictions, we will go to cross equation restrictions later. Okay. We usually have cross equation restrictions in the simultaneous equation models. Okay. Okay, this is the structural equation, the first structural equation. Y gamma 1 plus Z delta sub 1 plus U sub 1 is equal to 0. Okay. So Y here is 1 by G. The associated coefficients is G by 1. Z is 1 by M. Delta sub 1 would then be M by 1. Okay. First impose a normalization restriction that one of the elements in gamma sub 1 equals to minus 1. So we want one of the elements of gamma sub 1 to be equal to minus 1. This defines the left-hand side variable. For example, if in the first equation we have gamma sub 1, 1 is equal to minus 1, then we have the following. Okay, okay, so we have, note that in this form, we would have 0 is equal to gamma sub 1, 1, y sub 1 plus gamma sub 1, 2, y sub 2, and so on. Okay. But if we impose the normalization restriction, gamma sub 1, 1 is equal to minus 1, then you can put y sub 1 on the left-hand side. Okay. So earlier I asked you to do some expansion of this this one. So for you to have a feel of how this looks, I want you to express, well, 2 or 3 of the equations in a similar form, okay? Okay, so what does this normalization do? It means that we cannot get an admissible structure by multiplying through by any non-zero constant. Okay. Otherwise, we would have some indeterminacy. Okay, so that's the normalization restriction. You have to do that before doing before checking the rank condition. Okay. Okay, do you have questions? Do you have questions, Nan?
None. So
Yeah. Okay. You haven't taken this in 232 or 231?
Not yet po, ma'am.
Okay. Okay. Maybe I'll stop here since this can be quite confusing. So on Thursday, I'll go through the rank condition, the order condition, and the estimation. And if we have time, the cross equation restrictions and covariance restrictions. Yeah. Well, I was quite hesitant to go into simultaneous equations, but I think it's good to is in some sense it's good because it also reinforces what we had for instrumental variables, which we discussed in the framework of endogeneity. So for example, for the two equation system of simultaneous equation model, you can also already see some parallel with what we did using two-stage least squares. And also the reduced form, you can more or less see in two-stage least squares is similar to what you do at the first stage of two-stage least squares. There are, I guess, and also this brings out the problem of identification. Okay, so as you go into more econometrics, you always would bump into problems of identification. Okay, so I'll stop here and we'll meet on Thursday. Okay. So it's not really that difficult. The notation can seem to be messy, but as you work on it, you'd become more comfortable with the notation. And also the concepts are similar, really. They're just repeated applications of the same concepts, right?
Ma'am?
Yeah.
Is there already a schedule for the midterm?
I was looking at that. Well, I'm revising the sequence of topics. After simultaneous equations, I'll go into panel data. And it would be after panel data where we would have the midterms. I think I'm behind schedule. So most likely the midterms would be after the reading break. Okay. Because I think we just have about 3 weeks of classes, then we have the reading break. Okay.
Yeah.
I'll try to find some simpler approach to panel data approaches. The one of field bridge seems to be quite complicated. Okay. Okay. Yeah.
Is the midterm during a class? Is it during class hours?
Most likely not, because our class hour is just 1.5. So you would need at least 3 hours. Okay. Okay. Other questions? Okay. So I'll see you Thursday. Okay.
Thank you po.
Okay.
Thank you po, ma'am.
Ma'am.
May class pa kayo